Welcome to a video on the flux form of Green's theorem. The goal of the video is to determine the flux of a vector field in a plane. So if C is a simple closed, smooth curve oriented counterclockwise that encloses region R in a plane, where vector field F is equal to angle bracket F comma G, both having continuous partial derivatives, then the flux is equal to the line integral of F dotted with N, where N is a unit normal vector, integrated with respect to S, or arc length, which is equal to the double integral over the region R of div F differential A, where div F is equal to the partial derivative of F with respect to X plus the partial derivative of G with respect to Y. Again, this is called the flux, and it measures the flow across the curve C. So if the flow is outward, the flux will be positive, and if the flow is negative, the flow will be inward. This is similar to Green's theorem, except flux integrates the perpendicular or normal parts of the vector field, while Green's theorem integrates the tangential part of the vector field. So you can think of Green's theorem measuring the rotation or twisting of the vector field across C, and the flux measures the flow inward or outward across C. Let's go ahead and take a look at an example, and we'll also look at it graphically. Here we want to measure the flux of a vector field with components negative x, negative y across the circle x squared plus y squared equals 16, and here we'll assume the orientation is counterclockwise so that we satisfy the conditions needed to apply the flux form of Green's theorem. Let's go ahead and sketch our curve. So we have a circle with radius 4 and a counterclockwise orientation. Let's take a look at this surface in the vector field given. So here's our circle with radius 4, and here's the vector field, and you can see the direction of this vector field is pointing inward toward the circle, so we should anticipate a negative flux. Let's go ahead and calculate it. So we'll have the double integral over the region where the integrand is the partial derivative of f with respect to x. That's going to be negative 1 plus the partial derivative of g with respect to y. That's also going to be negative 1 dA. And because our region is a circle, let's go ahead and integrate this using polar coordinates. So we'll have negative 2, and then differential a is equal to r dr d theta. And then for the limits of integration, r will be from 0 to 4, and theta will be from 0 to 2 pi. So we're going to have negative 2 times r squared over 2, just negative r squared, it's going to give us negative 16 minus 0, that's going to be negative 16. So subbing in 2 pi, we're going to get negative 32 pi, and when theta is 0, we have 0. So our flux is equal to negative 32 pi. And again, because the flux is negative, it does verify that our flow should be inward across this circle. And again, if it was positive, the flow would be outward. And that's going to do it for this video. We will revisit this idea of flux in 3 dimensions in a future video. Thank you for watching.